Hi to all. Today's topic is mutual induction. It is a topic in electromagnetic induction chapter. Then what is mutual induction? Previously we discussed about the self-induction topic. Now I am going to explain the mutual induction. Mutual induction means induction of EMF or current in a coil due to varying current in neighboring coil is called as mutual induction. That means, for example, here we are taking the two coils. This is the first one, coil 1 and the coil 2. The coil 1 has the number of turns N1 and area of cross section A1. The coil 2 has the number of turns N2 and area is A2. Then here, whenever the current changes in the coil 1, the field generated by the coil 1 changes and flux generated by the coil 1 changes. That flux link with the neighboring coil, then due to that what happens when the flux link with this coil changes, then current and EMF induces in this coil and the galvanometer shows deflection. That means here the galvanometer shows the deflection when we close the plug key or when we open the plug key, because while closing and while opening the current changes in this first coil. When current changes in the first coil, the EMF induces in the second coil. This phenomena is called as mutual induction. That means induction of EMF in one coil due to varying current in neighboring coil, right? And when the current changes in this coil, field changes, flux changes. That change in flux link with the nearby other coil. Whenever the flux link with the nearby coil changes, then EMF induces in the nearby coil according to Faraday's law. Then our aim is that we are I am going to explain what is mutual induction and what factors this will depends, and that all things we are going to discuss. And then for that purpose, first the flux link with the second coil, right? I want the N2 what here? N2 is what? Number of turns in second coil, right? Number of turns in second coil. N1 is what? Number of turns in first coil. Number of turns in second coil, right? What is N1? N1 is also number of turns in first coil, right? And what is A2? Area of cross section of second coil. Area of cross section of second coil, okay? And A1 is the area of cross section of first coil, okay? Right. I want the flux link with the second coil, okay? Magnetic flux link with the second coil. Magnetic flux link with the second coil. Link with the N2 turns of second coil. Yes, what is it? That is N2 phi 2. That N2 phi 2, the flux link with this phi 2 is the flux link with one turn of the second coil, and N2 phi 2 is the flux link with the N2 turns of second coil. That will depends upon the current in the first coil. When the proportionality is removed, we will get a constant. The flux link with the second coil depends upon the current in the first coil. When the proportionality is removed, we will get a constant, that is M21 into I1. This is the important equation, right? And we can draw one box for this. And this is equation 1 we will take, okay? In this, when we remove the proportionality, we are getting one constant, that is M21. This is called as mutual inductance. Mutual inductance. Okay, mutual inductance in coil 2 due to coil 1. Due to coil 1. Okay, and here next I want whenever the flux link with the second coil changes, okay, EMF induces in the second coil. If you want the induced EMF in the second coil, then what we write? Induced EMF in second coil. Yes, that is E2. E2. That is according to Faraday's law, we know minus N2 into d phi 2 by dt, right? Okay, induced EMF in the second coil formula is E2 is equal to minus N2 d phi 2 by dt, right? Then in this we write as here E2 is equal to minus d by dt of N2 phi 2 also we write. This is according to Faraday's law we are writing, right? This is Faraday's law, right? Faraday's law. And here N2 phi 2 we know from equation 1 we write induced EMF as minus d by dt of we write as N2 phi 2 as M21 into I1 we can write. This M21 is a mutual inductance proportionality constant we write outside, that is M21 into dI1 by dt we write. That means induced EMF in the second coil E2 depends upon the rate of change of current in the first coil dI1 by dt. I1 is the current in the first coil and I2 is the current in second coil. Okay, induced EMF in the second coil depends upon the rate of change of current in the first coil. This we can take as equation 2. If you want to define the mutual inductance, either we can define by using the equation 1 or equation 2. Okay, right. Let us see here. We want to define the mutual inductance. Okay, then I am going to rub this and you take a screenshot. Okay, and note it every point due to this one is in. Okay, take a screenshot and note every point, and then after that I will continue. Okay, right? Can I? Okay. Okay, I want the definition of M. I want the definition of M, mutual inductance definition. Okay, define mutual inductance, right? Define mutual inductance. How we can define the mutual inductance? Mutual inductance we can define like this, right? Remember it. Okay, from equation 1 we write one thing like this. From equation 1 we write M formula, mutual inductance of second coil with respect to first coil. We write as N2 phi 2 by we write as I1. Okay, N2 phi 2 by I1 we can write. This is phi 2 is what it here, this is the flux link with the N2 turns of the second coil. Phi 2 is the flux link with one turn, flux link with each turn of coil. Flux link with each turn. Okay, right. Each turn of second coil. Its formula is like this, it will be there. Phi 2 is equal to B2. But the flux link with the second coil depends upon the field of first coil. That's why B1 A2 we write as cos theta. Okay, right, like this. And then here we write if the current is unit current, then magnetic flux link with one coil per unit current in another coil is called as mutual inductance. It was very easy. Okay, magnetic flux link with one coil due to unit current in neighboring coil. Okay, neighboring coil is called as mutual inductance. Mutual inductance. This is the definition that is based on equation 1. We can also define based on equation 2 also. We can write from equation 2, we write like this. From equation 2 we write M21 formula, right? That is, we write as E2 by di1 by dt, right? If di1 by dt is 1, if di1 by dt is 1, then M21 is equal to E. If you can take the magnitude only, right? The mutual inductance equal to induced EMF, when the induced EMF definition, the induced EMF in one coil due to unit rate of change of current, due to unit rate of change of current in neighboring coil is called as mutual inductance. Like this we can define in any way, right? This is about mutual inductance. Okay, and take the screenshot and note it, and then I will continue. This is the situation we discussed when current changes in the first coil, the EMF induces in the second coil. But if the current changes in the second coil, then EMF also induces in the first coil. Okay, that will also happens if you go for like that. Okay, right. Let us see here. This is the first coil. This first coil have the galvanometer. No battery in the first coil, right? And this coil has the number of turns N1 and area of cross section is A1. And another coil, right? This is the coil. Its number of turns N2 and area A2. And in this there is a battery, right? And there is a plug key. When we close the plug key, then there is some current in this. The current we can take it as I2 in this. Okay, now when the current changes in the second coil, this is the second coil, the magnetic flux link with the first coil will changes, right? Then we write like this. Okay, from figure, right? Flux link with the magnetic flux link with the first coil. Magnetic flux link with first coil. Link with first coil. What we write? Magnetic flux link with first coil is N1 okay, with one turn 5-1, with N1 turns N1 5-1. It depends upon the current in the second coil. When the proportionality is removed, we will get a constant, that is M12 into I2. This is the induction in first coil due to varying current in another coil. The key. Now look at here, the flux link with the first coil depends upon the current in the second coil. When the current changes in the second coil, the flux link with the first coil changes. Due to that, EMF and current induces in the first coil. Right? That's why this is the induction in first due to second. This M12 is called as mutual inductance. Mutual inductance in first coil due to second coil, right? This is about mutual inductance. And now let us see here, this is, we can consider as equation 3, right? Equation 3. And now induced EMF in first coil I want. And what is 5-1 here? 5-1 is the B flux link with each turn of coil, okay? Flux link with each turn of coil. Flux link with each turn, magnetic flux link with each turn of first coil, means only one turn. Okay, one turn. With one turn, how much flux links? This we can write as 5-1 as, this depends upon the field generated by the second coil. Flux link with the first coil depends upon the field of second coil. B2 we write as A1 B2 A1 cos theta we write. Okay, it's formula. And induced EMF in first coil I want. Induced EMF in first coil, that is due to varying current in second coil. This we write as induced EMF in first coil is E1, we write as minus N1 d phi 1 by dt. The induced EMF in first coil depends upon the change in flux in the first coil. This we can write as minus d by dt of N1 phi 1. And from the equation 1 we write N1 phi 1 as M12 I2. Okay. Now once again you take the screenshot and note every point. Right, let us see here. We can simplify that. Induced EMF in the first coil we can write as minus d by dt of N1 phi 1 we write as M12 into I2 we write. And this is from equation 3 we write. And you write here induced EMF as minus M12 into dI2 by dt we write. That means induced EMF in first coil is directly proportional to rate of change of current in second coil. Okay, and it also depends upon the mutual inductance. This is equation 4. Right? Now from equation 3 and equation 1 and equation 2, equation 1 and equation 3, we write one thing. If coils are closely packed, coils are closely packed. Okay, we can write M12 is equal to M21 is equal to M. This M is called as mutual inductance between two coils. Between two coils. Okay, right. And here the induced EMF in first coil, induced EMF in one coil is directly proportional to rate of change of current in neighboring coil. Okay, right. This is the thing, and we discussed in this flux link with for one coil depends upon the current in the another coil, that is N1 phi 1. Flux link with first coil depends upon the current in the second coil. Then here we got when flux link with the first coil, EMF induces in the first coil. That's why we set mutual inductance on the first coil due to second coil. When the proportionality removed, we will get constant. Similarly here, when the flux link with the second coil, if you go for, it depends upon the current in the first coil. Right? And these are the derivations. Let us discuss one problem and later I will close. Take the screenshot and note it, and I am going to rub total. Okay, now let us go for the solution of this problem, and it was very easy. And let us see here what they gave in the question, right? An EMF 0.5 volts is developed in second coil when current in the primary coil changes from 5 ampere to 2 amperes in 300 milliseconds. What is the change in current? 5 ampere to 2 amperes. We write 2 minus 5, that is a minus 3 amperes is the change in current. In time dt they gave us dt, that is a 300 milliseconds. This you can convert into seconds, that is 300 into milli means 10 power minus 3 seconds. Okay, right. Next, calculate the mutual inductance between the two coils. This is our question. Induced EMF formula we write as M di by dt, right? m di by dt. Induced EMF in second coil depends upon the rate of change of current in the first coil. Here we substitute all values. Induced EMF is 0.5 and minus m we have to calculate. The di by dt, di is minus 3 by dt is 300 into 10 to the power of minus 3. And now this we have to simplify, and for that we will get like this 300s, right? And then next step we will get like this, that is a minus minus will cancel, 0.5 is equal, we will get as m by what's remaining at here, 100 into 10 to the power of minus 3 is nothing but 10 to the power of minus 1. I want the m, then we take this 0.5 into this 10 power minus 1 goes to this side, and then finally we will get the m value as 0.05. M unit is the same as L unit, self inductance or the mutual inductance, that is a 0.05 Henry. And I am giving the one homework problem for you, and write its answer in the comment box and try for the solution. Okay, try it yourself what they gave in the question. Okay, you can read yourself what is the mutual inductance of pair of coils. Here also we have to find out the m. If the current changes, if a current change of 6 amperes in one coil causes the flux in the second coil of 2000 turns to change by 12 to 10 to the power of minus 4 Weber per meter. Weber per turn, not. I think I will I will look at the question once again. Weber per turn, not this per meter. This is the Weber per turn. That means when the current changes in one coil, the flux link with each turn changes by this much. When there is no current in the first coil, then at that moment there is no change in flux in the second coil. But when the current changes, then the flux changes. The change in flux they give, and think yourself. And there are not having more formulas. Either you have to use this formula n phi is equal to mi, or otherwise you have to use E is equal to minus m di by dt. There are two formulas only we have. Okay, check which formula is suitable and what we have to find out. Okay, right. Thank you for watching my lectures.